Welcome back. Today we're going to reorder routes to make all paths lead to City 0. There are n cities numbered from 0 to n-1 and n-1 roads such that there is only one way to travel between two different cities. This network forms a tree. Last year, the Ministry of Transport decided to orient the roads in one direction because they are too narrow. Roads are represented by connections, where connections I equals AI BI represents a road from AI to City BI. This year, there will be a big event in the capital, City 0, and many people want to travel to this city. Your task consists of reorienting some roads such that each city can visit the City 0. Return the minimum number of edges changed. It's guaranteed that each city can reach City 0 after the reorder. Okay, so if we have this graph, we have a 0 and a 4 and a 5. Over here we have a 1 and a 3 and a 2, and then we go there's roads connecting this way. 2 is connected to 3, 4 is connected to 0 but also connected to 5. Okay. Constraints and edge cases. There are at least 2 nodes, so I don't have to worry about what if the first one is null. And connections are always equal to n-1. 2 is less than, n is at least 2, and connections are equal to n-1. That is 1, 2, 3, 4, 5. There's 6 cities. Okay. So that makes sense. One road per city except capital, which means there's at least one city, or one road, because there's 2 cities. Connections dot length is equal to 2, so each connection has 1. Each connection has 1 link. Links 2 cities. That's a better way to say it. Links 2 cities. And then AIBI is one of the cities. AIBI is not itself. Okay. Edge cases. The only edge case I could think of is if a city is not connected, but they've established that every city is connected. Every city can reach the capital, but it doesn't have to reach the capital directly. Okay, so in this case, we have to reverse these 3. So what I'm thinking is that we can do this recursively. We look at number 1, and then we're going to call every child of the root. And if the arrow goes away from the root, then it gets reversed. Then we recursively call each child, and from the child to the next, we're going to count those as needing to be reversed. So let's do 1, 2, 1, 0, 1. So this turns out to be 3. Okay. So yeah, I think the problem is just how many roads are pointed away from, because we can't reorient any of the roads, or we can't change any of the roads, we only reorient them down to up. So this means I'm going to need a data structure that'll give me this path. So I'm thinking I use a dictionary, but that brings up a different problem. So if I do 0 and its children, let's see, what are the edges here? 0 has a 4, 0 edge, and it also has a 0, 1 edge. And then 1 has a 1, 3 edge. And a 0, 1 edge. Two has a 2, 3 edge, and that's it. 3 has a 1, 3 edge and a 2, 3 edge. 4 has a 4, 0 and a 4, 5. 5 has a 4, 5. Okay, so actually, no, I was going to say, what if I just go, if it's greater than, it's pointing up, but that's not always the case. So, I need to figure out how I know which ones should be reversed. So I go to 0, and I expect that 0 will be in the second place for both of them. So I can do that. So if I count this one, now I want to call 4 and 1. So at the start with 0, and then I want to do 4 and 1. At 1, I notice that I think 1 should be in the second place. Let's see if that works. So if 1's not in the second place, I can count here. And then that tells me for every one where 1 is not in the second, no, maybe I just need to add this to a list. So for this one, I have to call both 4 and 1. So I'm checking them all, building a list of nodes that aren't 0. Here, if I build a list of nodes that aren't 1, I end up with 0. What if in that case I create a set of already visited? So here I'm going to mark 0 as visited. And then on this level, I'll mark 1 and 4 as visited. And so 4 is going to check 5. And 1 is going to check 3. Because 0 is visited already. Okay, and then going to 3, we have 3 is in the second place for both, so we're good there. And we haven't visited 2, so we're going to visit 2 there. Meanwhile, over at 5 is in the second place, so that's good, and we've already visited 4, so we're done there. Okay, I think this is looking good. Let's pretty this up a little bit. And here we have 5 and 2, 3. There. With this being a depth first search, it shouldn't be a problem because everything, the cities don't connect to more than 1 because otherwise they wouldn't have enough roads, or more than 2 rather. Okay, so I think this is my plan. First thing I want to do is create a dictionary. So we're going to go connections equals empty dictionary, and then for edge in connections, we'll place both So we'll go Connex edge 1 and Connex edge 0 equals edge. No, what I need to do is make sure there's a key in the dictionary first. So if edge 0 not in Connex, Connex edge 0 equals empty list. If edge 1 not in Connex, Connex edge 1 equals empty list. And then Connex edge 0 dot append edge Connex edge 1 dot append edge. Okay, so each edge gets appended to every item it's attached to. Okay, each city it's attached to. And then we're going to create a visited list. Visited equals set. Okay, so now we're going to do, starting at 0, let's define DFS. And this takes a city, which is an int. Which means we need to do a count equals 0. Okay. DFS, so we're going to go for edge in Connex city if edge, let's see, we're counting the bad ones. The bad ones are where the parent is in position 1. So if edge 0 equals city, count plus equals 1. Else DFS edge 1 0. Can I do that? No, because I still have to DFS the second one as long as it's not in visited. Okay, so if edge 0, let's go for end in edge. If end not in visited, visited. Let's see, we're dealing with Python sets. Python, I think it's .add. Sets. Look at the set function. I'm gonna do union. No. Update add element. That's what I want. Visited dot add end and then DFS edge. DFS that edge. Okay. So that should do it as far as that functionality. So then I just have to call DFS 0 because we're always starting at 0. Return count. Okay, I think that'll do it. Test it out now. And we got an error because set cannot be, oh, lowercase set. Oops. Okay, cannot activate count where it is not. Okay, the proper way to do this, of course, is to make it a class variable. In which case, this dot, it's not this, it's self.conks. And then visited self.visited. And then self.count. Okay, maximum recursion. I am not ending somehow. Oh, I forgot to indent. So it was calling DFS regardless. List out of range. List index. Edge is DFX edge. I don't want edge, I just want end. Wrong answer. Expected 3, I counted 6. So let's see what I'm counting. Print count edge and node city. Okay. What do we got going on? So we start with 0. We're counting 0 to 1, which is correct. And then for some reason we're counting 0 to 1 again. Is it because of this? For edge and self connects. Edge 0 is city, so we count that. Oh. But why would node still be 0 there? For end and edge. Oh, it's hitting 1 and then hitting 0. That still shouldn't matter. Let's print DFS. Run. Yeah, so I'm doing a DFS on 0 apparently. Maybe that's it. I need to add visited at the top. There we go. Let's try that. Cannot access variable end. No. We will add city to the visited. Okay. I am getting 5 now. That's a little better. Okay, so at node 0, I correctly count 1, and then I DFS. At node 1, I correctly count 1, and then I DFS twice. That shouldn't happen. Let's do print count. Oh. Print self.count. Run. Okay, so it's here at 2.3. I'm on node 2. And I'm counting this one because edge 0 is 2. Oh, that's the problem. I shouldn't be counting the end, which is anyone who only has one connection. Right? No. That becomes a problem. Oh, how do I know that there's only one connection out? Well, hold on. I visited 2 before I picked up 2.3. So why isn't it saying, hey, this is a self.visited? Because I didn't check that in the right spot. So the easy thing to do is going to be and self.const city length greater than 0, greater than 1. But I think that'll break other test cases. Length const city list an int. This is supposed to be there. Okay. Oh, it almost made it, but it also didn't work. So I think I'll need to dig deeper on this one. So I will catch you later. And I'm back. My solution was pretty terrible. It beats 5% of attempts. The problem I was having was I didn't want to check visited nodes. I wanted to check visited connections. So the visited set contains edges converted to string. And as soon as I check an edge, if I've already visited it, I continue. Otherwise, I add it to the visited list and then go through my spiel. I had to bring the variables inside the function because the whole test case uses one class, one instance for all of it. And that's the solution. So I took a look at the competing solutions, and I think it's just about using data structures like queue instead of rolling my own. So thanks for joining me.